In this video, we're going to introduce the last topic in numerical integration. And in particular, we're going to talk about Gauss Quadrature. So the Gauss integration scheme, which is known as Gauss Quadrature, is a very efficient method to perform numerical integration over an interval. In fact, if the function to be integrated is a polynomial of an appropriate degree, then the Gauss integration scheme produces exact results. The Gauss integration scheme has been implemented in almost every finite element analysis software due to its simplicity and computational efficiency. So this section outlines the basic principles behind the Gauss integration scheme. So Gauss Quadrature aims to find the least number of fixed points to approximate the integral of a function f on the interval from -1 to 1, such that the integral is approximated as a weighted sum of function evaluations. So these xi's are the integration points and wi's are the associated weights. So we aim to find the values of the w and the x to approximate the integral. So we're first going to introduce the method for integrals defined over the interval from -1 to 1 as shown here, and then we will show how to use a change of variables to alter the integration limits when desired. So the number of integration points and the associated weights are chosen according to the complexity of the function f to be integrated. Since the general polynomial of degree 2n-1 has 2n coefficients, it is possible to find a Gauss integration scheme with n integration points and n associated weights to exactly integrate that polynomial function on the interval from -1 to 1. So the figure on the next slide illustrates the concept of using the Gauss integration points to calculate the area under the curve for polynomials. And in the sections following, the required number of integration points for particular polynomials are presented. So here you can see we've got a first degree polynomial shown here between -1 to 1. And if we use one integration point, we're able to exactly calculate this integral because this area will end up matching with this area and we'll end up with exactly the correct integral. Here we've got a third degree polynomial which requires 2 integration points to exactly calculate the integral, and we'll show kind of how this comes about in the following sections. Here, and then we've got an example of a 5th degree polynomial showing with 3 integration points we're able to exactly calculate the integral as this weighted sum of the value of the function at those integration points. So for a first degree polynomial, the order is 2n-1, which is equal to 1, which means that n is equal to 1. So that means one integration point is sufficient to exactly calculate the integral for a first degree polynomial. So if we consider the function f of x is equal to ax plus b, then our integral is defined here. So the integral from -1 to 1 of ax plus b is equal to x squared over 2 evaluated between our integration limits, which is equal to 2 times f0. So for functions that are very close to being affine or first degree polynomials, a numerical integration scheme with one integration point, which is at x1 is equal to 0, and with associated weight of w1 is equal to 2, can be employed. And this would allow us to exactly calculate the integral for a first degree polynomial. So in other words, a one-point numerical integration scheme has the form that I is approximately equal to 2 times f of 0. For a third degree polynomial, here 2n-1 is equal to 3, so this means n is equal to 2. So 2 integration points are sufficient to exactly calculate the integral of a third degree polynomial. So if we consider a function defined here as a third degree polynomial, we want to find this integral from -1 to 1 of our function, and we can integrate this, which is 2a0 plus 2a2 over 3. So if we assume two integration points in the Gauss integration scheme, we have the form shown here. So our integral is approximated as w1, so the first weight times the function evaluated at our first integration point, x1, plus w2 times the function evaluated at our second integration point, x2. So this is just rewriting those two equations. So if we want the Gauss integration scheme to yield accurate results, or the exact integral for this function, then the right-hand side of these two equations needs to be equal for any choice of a cubic function. So this has to equal this if we want these two integrals to be the same. So this means that the multipliers of all of our coefficients a0, a1, a2, and a3 should be the same. So basically what we're saying here is that this value, or the multiplier here, should be equal to the multiplier of all of our a0 terms. The multiplier of our a2 should be equal to the multiplier of our a2 terms here. And same with our a1 and our a3 terms. So this allows us to write four equations and four unknowns. So this means that w1 plus w2 is equal to 2, looking at our a0 terms. w1x1 plus w2x2 is equal to 0, looking at our a1 terms. w1x1 squared plus w2x2 squared is equal to 2 over 3. This is from looking at our a2 terms. And then w1x cubed plus w2x cubed is equal to 0, looking at our a3 terms. And then solving these, we find that x1 is equal to minus 1 over the square root of 3, and x2 is equal to 1 over the square root of 3, and w1 and w2 are both equal to 1. So this means these are our two integration points, and these are the associated weights. So for functions that are very close to being cubic, the following numerical integration scheme with two integration points can be employed. So we can estimate our integral I as f at negative 1 over the square root of 3 plus f at 1 over the square root of 3. So this was, again, just comes from wi f at w1 at f at x1 plus w2 f at x2. For a fifth degree polynomial, we have 2n minus 1 is equal to 5. So this means n is equal to 3. So 3 integration points are sufficient to exactly integrate a third degree or a fifth degree polynomial. So consider our fifth degree polynomial shown here. We want to evaluate this integral. So this is the exact integral as shown here. And if we use 3 integration points in the Gauss integration scheme, we get the expression shown here. So we've got this weighted sum of our function evaluations at our different integration points. So for the Gauss integration scheme to yield accurate results, again, the right-hand side of the two equations on the previous slide need to be equal for any choice of a fifth order polynomial. So this means the multipliers of a0, a1, a2, a3, a4, and a5 should all be the same. This gives us 6 equations in 6 unknowns, as shown here. And then solving this, we find that our 3 integration points are x1 is negative the square root of 3 over 5, x2 is 0, and x3 is square root of 3 over 5. And our associated weights are 5 over 9, 8 over 9, and 5 over 9. So functions that are very close to being fifth order polynomials, the following numerical integration scheme with 3 integration points can be employed. So it's this weighted sum of our function evaluation, so 5 over 9, f of our first integration point, negative square root of 3 over 5, plus 8 over 9 times f evaluated at 0, plus 5 over 9 times f evaluated at square root of 3 over 5. For a 7th degree polynomial, n is equal to 4, so 4 integration points are sufficient to exactly integrate a 7th degree polynomial. So following the same procedure that we've shown in the previous slides, the previous cases, the integration points and associated weights are shown here. And similarly, we can use this weighted sum of the function evaluations to approximate the integral. So this is for a 7th order polynomial with 4 integration points. For a 9th degree polynomial, we need 5 integration points to exactly integrate it. So following the same procedure again, these are the 5 integration points and associated weights. And this is the 5 integration point Gauss Quadrature scheme. For an 11th degree polynomial, n is equal to 6, so 6 integration points would be sufficient to exactly integrate that. Following the same procedure again, these are the 6 integration points along with the associated weights. And this is the 6 integration point Gauss Quadrature scheme. So Gauss Quadrature is very easy to implement and provides very accurate results with very few computations. However, one drawback is that it is not applicable to data obtained experimentally, as the values of the function at specific integration points would not necessarily be available. So it's important that we have the form of the function so that we can evaluate it at those specific integration points. So this is how it can be implemented in MATLAB. For example, so all of these here, just entering in a cell array with showing the integration points as well as the associated weights. So each cell is for the different numbers of integration points. So the first cell uses 1 integration point, the second one uses 2, the third uses 3 integration points, 4 integration points, 5, and 6 integration points. And then within each of those cells, the first is just a matrix is defined. And so the first row is the integration points, and the second row is the weights. So for 2 integration points they were minus 1 over the square root of 3 and 1 over the square root of 3, and the weights were 1 and 1. And similarly down. So just following the procedure that we just went through, that's how you can find what the integration points are and the associated weights, and then you can just program them into a table like this that you can look up for various, for the number of integration points that you're interested in. So then this function would accept the function as well as the number of integration points that you want, and then just calculates the estimate of the integral as this weighted sum of function evaluations at the specific integration points. So let's look at an example. We want to calculate the exact integral of cosine of x on the interval from -1 to 1 and find the relative error if we use the Gauss 1, 2, 3, and 4 integration point schemes. We also want to calculate the number of rectangles required if we use the midpoint rule for the rectangle method to produce an error similar to that produced by the 3-point Gauss integration scheme. And then finally, we want to evaluate the integral using the midpoint rule of the rectangle method with the obtained number of rectangles. So this is just a graph of what the function looks like and the integral that we are interested in. So the exact integral is just sine of 1 minus sine of -1, so 1.68294. So employing a Gauss integration scheme with one integration point, the form is I is equal to W1 times cosine of x1. So W1 was 2 and x1 was 0, so it is just equal to 2. And our error, our relative error here is equal to negative 0.1884. So this was our exact value minus our estimate divided by our exact value. So now we can do the Gauss integration scheme with 2 integration points. So here we've got I is equal to W1 cosine x1 plus W2 cosine x2. So plugging in what we know for W1 and W2 and x1 and x2, the integral is approximated as this weighted sum of our function evaluations at our integration points. So it's 1 times cos of -1 over the square root of 3 plus cosine of 1 over the square root of 3, which gives us the result here, and we can calculate the relative error as shown here. With 3 integration points, we have I1 is W1 cos x1 plus W2 cos x2 plus W3 cos x3. Just plugging in our values of our W's and our X's, as shown here, we get the estimate 1.683, which gives us a relative error as shown here. With 4 integration points, we have that our estimate of the integral is w1 cos x1 plus w2 cos x2 plus w3 cos x3 plus w4 cos x4. So plugging in our weights and our integration points, we find that the integral is 1.68294, which is has an error estimate of 1 times 10 to the negative 7. So using the MATLAB script, this is the result produced. So you can see with only 4 function evaluations, we're getting a very good approximation of the integral. So let's take a look at if we use the rectangle method instead. So with the 3-point integration scheme yielded an absolute error of 0.00006. So if we recall the error estimate for the rectangle method, the midpoint rule of the rectangle method, and we want to find the number of, or the h required to achieve the same error, the same upper bound of our error. So we know b minus a is equal to 2, and this max of f double prime c would be equal to 1 for this function. So that means h is equal to 0.02683, which means that the number of required rectangles is approximately 75. So with 75 rectangles, the midpoint rule yields an integral of 1.68299. And so we can note how accurate Gauss integration is compared to the rectangle method. So it would take 75 divisions, or 75 integration points, to reach an accuracy similar to the Gauss integration scheme with only 3 points. So the Gauss integration scheme is incredibly efficient and accurate compared to something like the midpoint rule. So far we've only presented the Gauss integration scheme for functions that are integrated over the interval from -1 to 1. But of course, in many situations, you would want to be able to evaluate the integral over any other integration limits. So we'll just go through how we can set this up for alternate integration limits. So a simple change of variables can be used to allow us to integrate a function g of z, where z is on the interval from a to b. So in this case, the linear relationship between z and x can be expressed as shown here. So z minus a divided by b minus a is equal to x minus the lower limit, which was -1, divided by the upper limit b, or the upper limit 1 minus the lower limit -1. So just simplifying this right-hand side, we get that this is equal to x plus 1 over 2. And this can be rearranged as shown here to find that z is equal to b minus a over 2x plus b plus a over 2. So this is our function, our z as a function of x. So z as a function of x is equal to the expression shown here. So b minus a x plus b plus a over 2. So just combining those two fractions into one. If we take the derivative of this, or find is dz is equal to b minus a over 2 dx, which means that the integration can be converted from integrating over z to integrating over x as shown here. So if we have this integral g of z dz, we can change the dz into b minus a over 2 dx, and then we can plug in our expression for z of x into here. So we get that the integral of g of z from a to b can be evaluated as the integral of g of all of this, b minus ax plus b plus a over 2, times b minus a over 2 from the integral from -1 to 1. So that means we basically do this transformation, and then we can use our Gauss quadrature on this expression, or this function, to evaluate the proper integral that we're interested in. So then the integration can proceed as per the weights and the values of the integration points with f of x given by the expression shown here. So f of x is this evaluating our g at all of this multiplied by b minus a over 2. So let's take a look at an example. So we want to calculate the exact integral of x times e to the power x on the interval from 0 to 3, and find the absolute relative error if with using 1, 2, 3, and 4 integration points using the Gauss integration scheme. So first, to differentiate between the given function limits and the limits after changing variables, we assume that the function is given in terms of z. So g of z is equal to z e to the power z. So the exact integral, we can evaluate this, is given as 41.1711. So using this linear change from z to x, we have the expression here. So we can just put in the values. So we know that b was 3 and a was 0. So we can just put those into here, and this gives us the expression here. And then this is evaluating g at 3x plus 3 over 2, which was x times e to the x. And then we're multiplying by our 3 over 2 here and still have our 3 over 2 here. So now this is written as the integral from minus 1 to 1. So we can use our Gauss quadrature on this expression. So employing the Gauss integration scheme with one integration point, we have w1 f of x1, which is 2 times f of 0. So we have to remember to plug 0 into our full function here. So we get 20.1676. And the associated relative error. Using 2 integration points, we just plug in our weights and our integration points. So the estimate of the integral is 39.607, and our associated error is 0.038. Using 3 integration points, again, we plug in our weights and our integration points. So our weights here were 5 over 9, 8 over 9, and 5 over 9. And if we remember to evaluate the function at the proper integration points, which were given in the beginning of the lesson, we get that I3 is equal to 41.1313. And an associated error of 0.000967, where these were the forms of all of our functions at the specific integration points. And we can also do it for 4 integration points following the same procedure. So using our MATLAB script, these are the results for using 1, 2, 3, and 4 different integration points, as well as the associated errors. And you can see with 4 integration points, we're getting an error of 1 times 10 to the minus 5.